Okay, great. Rakesh, are we live?
Yes, Mohammad.
Okay, hello everyone. Welcome to another lecture of PNS Modern SSDs. In this lecture, we are going to cover fine-grained mapping and multiplane operation over block management. So, as a quick recap, in previous lecture, we covered SSD organization, NAND flash organization and operation. We also cover some advanced NAND flash commands to improve the performance of flash operations. And we also, as one of the application or functionalities of FTL, we cover address translation and garbage collection. There are also other functionalities for FTL, such as I/O scheduling, that we are going to cover in next lectures. So today we are going to cover fine-grained mapping and multiplane operation over block management. Let's jump into fine-grained mapping. So we always, in this course, we talk about I/O mismatch between OS and NAND flash. So the page size in NAND flash, which is has continuously increased. It was like 256 bytes in the very beginning, but currently it's usually 16 kilobyte. Only except for some flash memories, flash chips that they are optimized for latency, like Zen and Samsung, that use small pages like 2 kilobyte or 4 kilobyte. Usually NAND flash chips, they use 16 kilobyte pages to reduce the area overhead, because this way, when you increase the page size, you can you can reduce the overhead of peripheral circuits by large pages. And also it improves the bandwidth. So basically it has some more latency when you want to read larger pages. But if you're able to use this this high large pages, then overall it can improve your bandwidth. So the logical block or sector size of file system, it has also increased. So it was like 512 bytes in the beginning, but now it's usually 4 kilobyte. So it is actually increasing. That is also important to work more efficiently with NAND flash-based SSDs. However, increasing the block size is not straightforward. Block size in the OS, because in the end, if you want, it is also the I/O handling is closely related to OS memory management, which we have memory page size is 4 kilobyte. So if you want to increase the I/O pages size, the logical block size, then you also need to basically have unnecessary fetch or eviction at the page cache, which is, I'm not saying that it is impossible, but it's also another trade-off. So it can work better probably for NAND flash, but it has some conflicts on other level of systems that in the end, basically it's not as straightforward, which is useful or not. So in SSDs, we have some small write request, which is less than NAND flash page size. So we know that basically it is well known that it provides some inefficiencies due to the raise before write property. But let's see it with some examples. So here, consider that we want to write to a logical block address 4 with size 1. So we want the number of basically the number of sector is 1, or number of blocks that we want to write. OS level I/O block is 1. So, and the data that we want to write is A. So here we want to only write one 4 kilobyte data at the starting address of 4. So this is you can consider this as the organization of the NAND flash, that we have several blocks. So here, for simplicity, we consider only 4 pages in each block, and each page is 16 kilobyte. So you can see that we have here some mismatch. So we want to write 4 kilobyte in a 16 kilobyte page. So if the mapping table, as we already covered, stored the data. It is a page level mapping. So basically, you can map a logical page address to a physical page address. That logical page address could be basically 4 kilobyte to 16 kilobyte, but page physical page address is always 16 kilobyte. So how we do that? Basically, when you write the logical block address in bit, we use the 2 least significant bits as the offset, because we have our pages is 16 kilobyte, but our request could be 4 kilobyte. So we can have 4 requests in one page. So in order to differentiate between them, we can use the 2 least significant bits in the address as an offset. And the rest of the address we can use as the page number, which is the 16 kilobyte page number. It is really, I mean, closely, you can also, if you are aware of the cache block in computer architecture, so cache block is also the same, right? When the address, usually the memory is byte addressable, but working, but the addresses in cache, we store them as a block. So whenever you want to read a word or read a byte from your cache flow, you can use your offset bits, right? So we have similar concept here also. So here we see that the page number is basically 1. So we want to write data A with the size 1, so which is only 1 4 kilobyte data in logical page address 1. So the FTL suggests the first free page, which is physical page address 0 in block 0. And then we write A, right? So here you can see that we keep the offset, right? So since the offset was 0 in our request, we also write the A as exactly in the offset 0 in that physical page address. And then we keep the metadata of that physical page address here. The next request is logical block address 1. So, and then the size is 2. So we want to write 2 pages, 2 4 kilobyte pages, but the data is B and C. So when you open write the logical block address in bits, you can see that the page number is 0, but the offset is 0 1, right? So in the mapping table, we can check the LPX 0 and then physical page address. So the FTS suggests the next available physical page address, which is page 1, physical page 1. And then we write B and C as exactly aligned to the offset that we have, right? So why we at the middle of the page? Because we want to keep the offset, which is I guess clear, because we don't keep the offset. We basically, if we write B at the beginning of the page, then we need to also keep some metadata for that. That this B is in another offset, but we decode the offset based on that the 2 less significant bits. So we keep the alignment in the physical page address. So why we couldn't use the free slots in the physical page address 0? Because we already mapped that physical page address to addresses from 4 to 7, right? Because addresses 4 to 7, the logical page number is 1, and then the offset is from 0 to 3. So we already mapped that in our mapping table, so we cannot use that. Is that clear so far? Okay, yeah. Great. So then the next request, we want to write to address 7. So when you write, check the bits, you can see that the logical page number is 1. So in our mapping table, we already have this metadata for page 1, right? That we already mapped to physical page address 0. So can we write here? Any thoughts? So the answer is not likely, because basically when we want to write to the operation, granularity write is page. So we already write a 16 kilobyte page. Even if we write, we consider that, okay, we don't want to change, we don't want to program the rest of, the 3-4 kilobytes remaining 4 kilobyte, let's say, space in that physical page address. We consider that we want to write 1, right? Because when we want to store 1 in a NAND flash cell, we don't program, right? So basically, with that, you can argue that, oh, we don't program that. So now we can program. But the thing is that we have data randomization. So basically, even if the FDL, for example, consider that it wants to write all 1 for the remaining 12 kilobyte space, after data randomization, then we don't have all 1, and we already programmed it. So we cannot use that before. Basically, we need to erase if we want to write in that physical page address. And the another reason is that we need to keep the program order. We have some constraint in program order, right? So reprogramming physical page 0 can affect the reliability of this data stored in the physical page 1, which is I guess we covered previously. So because of these 2 reasons, very likely we cannot use that unused space. So you can see that we have some unused yet discarded space. And these small rise cause waste of PE cycles, because more frequent garbage collection that cause performance and lifetime degradation. So how we can handle that? Basically, we need to first read that A in our DRAM, internal DRAM in SSD, and then modify that page with our new data, which is we write D in that position, and then we need to write the modified page in another physical page address, and also we need to update the mapping table, right? So basically, it causes waste of P cycles and also additional read operation, all because of these small write requests. So you can see that small write requests, which cause due to the I/O mismatch, that OS works with 4 kilobyte pages, but in SSD we work with 16 kilobyte pages, has performance and lifetime overhead. So how we can deal with that? Basically, the idea is simple. We keep the mapping based on 4 kilobyte, right? So we write a page only when there are sufficient data blocks. So let's see how it goes, how it works. We have so in the previous example, we want to write in logical block address 4. So here you can see that the mapping table is stored based on the fine grain, 4 kilobyte. So it's not based on 16 kilobyte. So whenever you want to find your metadata in mapping table, you only need to basically check the exact address. You don't need to basically remove the truly significant bits, consider them as offset, and then consider the rest as the logical page address. So we don't write A immediately in the SSD. We write A in the page buffer, which is, you can consider it as a DRAM buffer that we have in SSD. So we write A in that buffer and update the mapping table. So this updating mapping table also can happen later, but by later, I mean whenever you really want to write this data in SSD. But basically, yeah, regardless, we need to do that, but we can do it in advance or we can do it later. And then the next request, so logical block address 01. So we keep 2 slots in the mapping table because it has 2 4 kilobyte pages. And then also that the third request, which is 07, and also we write it in the page buffer. So now we have 4 kilobyte pages in our page buffer, and now we can do the write. So we flush the page buffer, which is in DRAM, to the SSD, and we write only 1 page write, ABCD. So with this fine-grained mapping, we significantly reduce the number of NAND flash operations. So in the previous example, we had 3 writes plus 1 read, but now we have only 1 writes, which you can see how efficient is fine-grained mapping. Any question here? Okay, cool. So, but there is no free lunch, right? So basically, this 16 kilobyte mapping that we had in before, the overhead is storing 4 bytes per 16 kilobyte page. The mapping basically information is around 4 bytes per 16 kilobyte page. That basically the overhead is 0.025%. But now with fine-grained mapping, we need to keep information based on 4 kilobyte data pages. And then we need 4 bytes per 4 kilobyte page, which you can see the overhead is 0.1%. And that's the main reason in the very beginning lectures, we were saying that the DRAM size in modern SSDs is usually 0.1% of the SSD, because commodity SSD or modern SSD, they use fine-grained mapping because it's really important to improve the performance and increase the lifetime of SSD. So, but yeah, it can come as the price make SSD more expensive and also power energy consumption for sure. And another problem is data durability of written data. So in your page buffer, or can be DRAM. So DRAM is volatile memory, but it can also store some, basically your dirty data, right? So because you write your data first in your page buffer, in your buffer, DRAM buffer, and then once you have sufficient number of pages, you flush the DRAM to the SSD. So once data is written to an SSD, the SSD needs to guarantee the data's integrity, even under sudden power off. So but when we have the data in our DRAM is volatile memory. So if we have sudden power off, how we can guarantee that? As we also covered previously, we need to have some capacitors to keep some charge in order to, whenever we have a sudden power off, those capacitors can provide enough charge to do this flushing operation, right? So we can keep the basically data's integrity. So, but this is, as you can see, this comes at a price. But yeah, despite non-negligible drawbacks and overheads that this fine-grained mapping has, basically fine-grained mapping is widely used in modern SSD due to its high benefits. Okay. Any question? Okay, let's move on to multiplane operation available block management. So we already covered multiplane operation. We know that we can have concurrent operation on different planes, but basically the constraint is that we can do that only for the same operation on the same page offset. So that's the constraint. So I move on quickly on this slide because I guess we all are aware of that. So in order to maximize the opportunity of this multiplane array multiplane operation, basically SSDs or FTL needs to do multiplane array data placement. So to perform as many multiplane operations as possible, we want to flush n pages, which is n number of planes pages at once after buffering them. So basically, when we have one write, we wait for more writes. And then when the page buffer is full, we flush to the NAND flash chip. And then the next one. So here we need to keep the write points of all planes to be the same, right? Because of the constraint of the plane that we need to have the same word line. So in order to do that, SSDs they use super block based block management. Let's see how it is. So another quick recap for reducing the performance overhead of garbage collection. The FTL can select the block with the largest number of invalid pages. We call it the greedy policy in the past lectures. So why is that? Why we do that? Basically, whenever we want to do garbage collection, we need to select a victim and then copy all valid pages in that victim block to another free available pages, and then make all pages in that victim block invalid, so that we can erase that block and then use it for future writes. So in order to reduce the number of reads of the read, basically copy operation, we want to one common practice is to maximize choose the victim based on that victim is a block that has the maximum number of invalid pages. So this is greedy policy. So in this example, we have some free pages, we have some valid pages and invalid pages in this plane. So we can see that block 2 has the maximum number of invalid pages. So we select it as victim, and then we copy the valid pages in that block 2 to block n-1. And then the all pages in block 2 is invalid, so we can erase it. And also, so the active block or write point is block n-1, and that victim block can also become active block once we need it. So remember that we do lazy write, lazy erase. So we don't, whenever we make a block all pages invalid, we don't erase it immediately. We wait for whenever we need it because of that open active block issue. So consider that we want to implement this operation, this greedy operation, in a multiplane flash dies. So here we have 2 planes in this die, and in each plane you can see that we have different number of invalid pages in block. So if we want to do this greedy policy, we need to basically consider basically we select block 2 in plane 0 as the victim, and block 1 in plane 1 as the victim in plane 1. So we need to basically do single plane read, and also another single plane read in that block, and then we can do multi-plane write, right? So in this block n-1 here. However, this block 2 it has 2 more pages, right? So we need to do 2 single plane reads, and 2 single plane writes in that block n-1 in plane 0 as well. So basically, how many copy we need here? So we have 3 active block, 3 active pages, 3 valid pages, let's say. Valid pages in block 2 and 1 valid pages in block 1, right? So overall, we have 4. So in reality, or in an ideal case, we need 4-page copy, which can be done with 2 multiplane reads and 2 multiplane writes. That's the ideal case, right? But here we need to do 4 single plane reads, 1 multiplane write, and 2 single plane writes. And in fact, it's not the only overhead. Another important overhead is that in block n-1, you can see that FTL cannot do multiplane writes unless it discards basically the page, the second and third pages of block n-1 in plane 1, right? Because in block n-1, we have the first 3 pages is valid, and after that we have 3 pages. But in plane 1, after page 1, we have valid 3 pages. So we need to basically the FTL needs to discard the first page second and third so that it can do multiplane operations. And also, that's not the end of the story. So after using block n-1, when the next active block becomes block 2 in plane 0 and block 1 in plane 1, then we cannot do multiplane operation as well. So you can see that if FTL is not aware of that multiplane operation and does not basically perform multiplane aware block management, how basically the overheads that we have in both in garbage collection and also in later writes. Okay, so now the concept of super block based management. So we group each block with the same index, or you can consider the block that they have in basically we can basically the same word line. So here and then we choose the super block that accumulatively has the maximum number of invalid pages. So here you can see that block 1, which is, let's say, super block 1, has accumulatively has 9 invalid pages. So we consider it as a victim. So we need to basically copy the valid pages. So you can see that we need to read 5, right? Because we have we need to read 5 single read in block 1 and 1 multiplane read, right? To read all valid pages. And then we can do 3 multiplane writes. It's a mistake here. So we need to we can do 3 multiplane writes in block n-1. And that's also we can buffer the last page in our DRAM and wait for another read, another write operation, so that we can also write that in using multiplane write operation. So we don't need to basically write that data immediately in super block n-1, because if we do the write immediately, we cannot use multiplane write operation. So the pros is that it keep performing multiplane writes, but sometimes it can actually increase the number of read and write operations. So here in this example, previously we had 5 single reads and 1 multiplane read and 3 multiplane writes, but now we have 4 single plane reads, 1 multiplane write, and 2 single writes. Okay. So basically, the concept of superblock can be also extended to more planes. It shouldn't be only in one die. You can have a superblock across different dies. So in here, we can have, for example, die 0, die 1, die 2. So we all consider, I mean, the blocks that they are in the same offset, we consider them as a superblock. But basically, it has, as I said, it has some pros and cons. So in reality, we don't know exactly how it is implemented in commodity SSDs. And basically, it's one of actually research direction to comprehensively study the design space of these superblock management in SSDs. So any question? Okay. If no, I think we are done with today's lecture. We will cover IO scheduling in next week, which is I guess the last meeting before Christmas and New Year. So yeah, see you all next week.